introduce you, and there's not much after that. I'll just mention that do you want questions at the end, or feel free to
on the fly is probably fine. I mean, there's not
Okay.
that many people here, so yeah.
So
But I can still try to finish a bit earlier or whatever.
Okay. I have to go run another session at the same time, apparently. So I'll introduce you, but then I'll have to disappear.
Okay, no worries.
But
Okay.
because I'm supposed to give a talk at
Oh.
this time. So anyway, yeah. Well. Like 1 more minute.
Okay, sounds good.
Nobody will step on it. Is it just the flashing that you're worried about?
Yeah, it kept going off. Even though we were still getting it at my recording. For some reason.
Okay.
Good to go? All right, thank you for coming, everyone. We're going to get started. So welcome to the tutorial section of Inform. So Will Ma was gracious enough to provide one of the tutorials this year. We have 12 of them this year. He's from Columbia, and he'll, hopefully this will not go out, but he's going to talk about randomized rounding approaches to online allocation, sequencing, and matching. And we're very excited to have him. So without further ado, take it away.
Okay, thanks a lot, Jamal, for the introduction. My name is Will. I'm an associate professor in DRO at Columbia Business School. It's a great honor to be able to give this tutorial here today. I'm going to talk about, I'd say, probably the technique, my favorite technique that I've used in my research, which is randomized rounding for online algorithms. Broadly speaking, I work on the design and analysis of online algorithms for e-commerce and revenue management applications. And I'd say this is like a pervasive tool that has often came up. So I'll try to give you hopefully some tangible takeaways, regardless of whether you're seeing this for the first time or you're a seasoned veteran who worked on this before, much before I did. So, all right, so let me dive right in. I'll start by talking about classical randomized rounding. I'm sorry that you'll have to pay really close attention because it's, the screen is only on half the time. But is it OK now? OK. OK, I'll just keep talking, and then we can. OK, good. So I'll start with classical randomized rounding first. So this is randomized rounding for offline discrete or combinatorial optimization problems. And I'd say this is how it got started, where we have it's not dependent on whether I click this button, right? It's just, I can also try emailing you the slides if that's easier. Or clicking a different button, or like, yeah. With this cable? Do you want me to email you the slides as a PowerPoint? OK.
Like a different adapter, maybe? I don't know if that's going to do it. I think it's mostly an issue with the surface.
Oh, I see. You can try changing this if that's helpful. Yeah. OK, seems OK. OK, fingers crossed. OK, so, maybe not. I can email you my slides if that's easier. OK. Sorry about this, everyone. It's a lesson that you should show up early. I didn't get here early enough. I need to email you my slides? OK. OK, it's on the drive. Do you want me to unplug this?
Yep, go right ahead.
Okay, cool. I can use my own clicker, or
OK,
that's fine. OK, this is fine. I don't need the thing yet. OK, cool. So, thanks a lot, everyone. So let's try this again. I'm very excited to talk about randomized rounding for online algorithms. It's not too loud, right? The speech, it's just very loud to me. So OK, I'm going to go deaf at the end of this. All right, so let me start with classical randomized rounding. So originally, this was used for like combinatorial optimization problems. So hopefully most of you have seen some kind of problem in this list before. I'd say very like founding problems for theoretical computer science and operations research, things like set cover, traveling salesman. So these problems, they're all discrete optimization problems that you can formulate as an integer program. But integer programming is often hard. So randomized rounding is one way to approximately solve integer programs, where what we do is we relax and then round. So relax means we write an LP relaxation where we allow the solutions to be fractional in the integer program. So you can think about the integer points being something like these red points, and then the LP feasible region being a polyhedron like this. And then the second step is to round a fractional solution to an integer solution. So classically, the challenge is you might have an extreme point that lies outside the convex hull of the integer points. So what you need to do is you need to kind of like figure out how to scale that solution to lie in the integer hull so that you can write it as a convex combination of integer solutions. All right, so that's classical randomized rounding. So what I'm going to talk about in this tutorial is what I call sequential randomized rounding for online algorithms. So the difference here is we're focusing now on online stochastic optimization problems where you don't know the entire input of the discrete optimization problem in advance. You have to make decisions on the fly, and you're given the correct probability distributions of future uncertainties. So the analog of the integer programming hammer here is dynamic programming. In principle, you can solve all of these problems using dynamic programming, writing a stochastic dynamic program. But now the challenge is cursive dimensionality. For a lot of these problems in online stochastic optimization, the state space will be exponential. So once again, we can take a relax and round approach where now we're relaxing the dynamic program to what's sometimes called an offline or fluid LP. So here we're collapsing the exponentially many state space in the dynamic program into a small state space by replacing random variables with their expectations. That's often what you do. So once again, you end up with a polyhedral region that you can compute. It might look like this blue thing. And now we're trying to round a fractional solution in this fluid feasible region online. What does this mean? So, I have a solution that I solve using my fluid LP. It might be this point. And now I got to decide whether to round coordinate 1 up or down. And the key thing here is that I can't just freely round it up or down. Whether I can round it up to 1 depends on some stochastic realizations. You can think about this for now as like, whether customer 1 has a high enough valuation. And moreover, I have to immediately decide whether to round this coordinate up or down without knowing the realizations of future stochastic random variables. And of course, if I round this up or down, it affects my feasibility of whether I can affect future variables up or down. So that's generally going to be the difference between online randomized rounding, where the challenge lies in having to round one at a time, subject to these stochastic restrictions, versus the classical randomized rounding. And I should say here, usually, the solution will lie in the polytope. The challenge isn't caused by this point lying outside the convex hull. In fact, usually you have these additional constraints where the probability, the x1 coordinate has to be at most a probability that 1 can be rounded up. So I'll try to now make this all precise. I'm going to talk about 3 examples in this tutorial. I'll start with some hiring problems, which are more simple. I'll talk about stochastic knapsack. And then I'll talk about online contention resolution schemes, which is a very active research area right now, motivated through an online fair allocation problem. And I hope that, I'll try to give you some sort of takeaways and some key intuitions that, in my mind, make sequential randomized rounding techniques kind of unique. So hopefully everyone will go home with something. OK, so let me start with hiring problems. I'm going to consider the following sequential offering problem that was formulated by Raghavan Purohit Golapudi in 2019. The problem is quite simple. So imagine I'm a hiring firm. I've already interviewed candidates, and these are the candidates that I like. So they all have some known value. I assume I know their value to the firm. And I assume I know the independent probabilities with which they would accept an offer if we make them one. I have k positions that are identical, so I can hire at most k candidates. And I sequentially make offers to candidates. When I make an offer, they immediately decide accept or reject according to these probabilities pi. And I'm trying to maximize my expected total value of hires. OK, so far this is not a very interesting problem. Does anyone see the optimal solution? Feel free to ask me questions on the fly, by the way. I think it's a good. So you do decreasing weight. Because you have nothing to lose by just trying the highest value person first. Even if they have a really low probability of accepting, you just then move on to the next person. So in this problem, there's also a constraint that you can make at most t offers. And now, suddenly, there's a trade-off where I could still do a similar strategy where I'd like to think, OK, I'm just going to make offers to the best candidates. This is good if I have a lot of time. But if my time is short and I need to fill the k positions, then I might want to consider the probabilities pi in making these decisions. All right, so a priori, if you try to solve this problem using dynamic programming, your state space would be exponential. It would depend on how much time you have left, how many positions you have left, and which subset of candidates you haven't offered to yet. So what we're going to do is we're going to solve it using this relax and round method. And here, I'm going to write the following linear program. You should think of yi as the probability that I make an offer to candidate I. And hopefully, the constraints are intuitive enough. It's saying the expected number of offers can't exceed t. The expected number of people who accept can't exceed k. And the objective is just to maximize the expected total weight of hired candidates. So a very common type of first step when you're doing this type of proof is you want to show that the LP objective value is an upper bound on any actual algorithm. These types of proofs are usually simple, so I'm just going to talk through the proof for this one. So essentially, the argument goes, OK, you give me any sequential offering algorithm that you think is optimal, or you give me the actual optimal one. I know that on every sample path, it has to satisfy these constraints if I replace these probabilities with the indicator random variables for whether you make an offer to I and whether I accepts. And then therefore, if I take the expectation on both sides, because it holds on every sample path, it holds an expectation. And then so therefore, if I let yi be the probability that the optimal algorithm makes an offer to candidate I, it'll form a feasible solution to this LP. And the objective will be exactly what the LP gives you. There's one slight trick. You need to show that the expectation of the product equals the product of the expectations. But that's where we needed the independence assumption, that whether the I accepts the offer is independent of anything you can deduce before making them the offer. And so that's essentially the argument. That's usually the first proof you write when you do a proof like this. You show that this LP is an upper bound on any actual algorithm. So if you can get, like, say, a half of the value of the LP, you get at least a half of the value of the best algorithm. OK, so that's the relaxation step. So now how do we actually round this? This is from some earlier work with my student, Boris, who's in the audience. So the first step of the rounding is we solve the LP. So I should note, the thing that you're rounding might not actually be the yi's that correspond to the optimal algorithm. But it doesn't matter, because this will give you an upper bound. The actual algorithm, we don't know what it is, so we don't know what the yi's are. OK, in this particular problem, we need a basic optimal solution. We'll see why. And essentially, the intuition in general when you're doing relax and round is you let the LP be your guide. So yi is supposed to be the probability that I make an offer to I. So first, if yi is 0 or 1, easy enough. I'm just going to decide to make an offer to I. So I'm going to let capital I denote the set of candidates I plan on making an offer to. And it's just going to be 1 if the fractional value is integer. All right, so this is where I needed the basic part. So there can be at most 2 fractional solutions. Why? Because there's only 2 inequality constraints here other than these. So once again, this is easy enough. So if there's 1 fractional solution, I just set capital Yi to 1 with probability yi. If there's 2, I know they have to sum to 1. Because if there's 2 in a basic solution, I know both of these constraints are tight. So the 2 fractional components sum to 1. And therefore, I can just set one of them to 1, satisfying these probabilities. OK, and then the algorithm is easy enough. Then I go back to Vish's suggestion, where I just sort by weight. And I just make offers to this set in decreasing order while positions remain. But the key thing here is there might be high weight, low probability candidates with yi equals 0 if my time is very short. And that's kind of what the LP is already capturing. The LP gives you a guide on whether you have enough time to chase after those long shot candidates. OK, so that's my algorithm. And the theorem is just for every problem instance, this algorithm is well defined. It makes the most T offers. And that's why it was important that we selected at most one of those fractional components to be 1. And now I'm going to show you that we get objective at least this factor times the LP, and therefore at least this factor times the value of any algorithm. Note that so this is going to be an increasing ratio. It's 1 minus 1 over e, which is about 63% of k equals 1. For large k, it actually approaches 1. The main intuition for this is just if the number of positions is very large, the law of large numbers works in your favor, and you have very low stochasticity in how many people are going to accept the offers you make. OK, so I'll try to give you a proof of this for k equals 1. So I'd also like to think most of the proofs I'm going to show you are reasonably simple. So this tutorial will have some proofs. OK, so I'll just prove this for k equals 1. We re-index the weights so that they're decreasing. So what I'm going to do is I'm just going to write, OK, this is the value I'm comparing against. I'm just going to rewrite it, essentially doing integration by parts. So the way to think about this is I'm going to write each weight wi as a sum of increments of how much better wj is than wj plus 1. OK, and this step is just integration by parts or switching sums, whatever you want. At the end of the day, it's like I sum over, essentially you should think about this as the probability that I hire candidate I or better, smaller indices are better, and I collect this gain from candidate j to candidate j plus 1 if and only if I hire a candidate whose index is j or lower. OK, so that's the LP. Now I'm going to analyze the algorithm and try to compare it to this expression. So I'm going to let pi be the indicator for whether candidate I would accept an offer. I can now write the algorithm's objective like this. So it's more complicated because the algorithm lives in the real world, not the fractional world, where you should think about piyi as this is a prerequisite to hiring I. Because this means yi was 1, I made I an offer, and pi is 1, I would have accepted. But that's not enough, because here I only have 1 position. So I needed everybody before I to have rejected, or sorry, to have not been hired. So basically, the indicator for me hiring I is piyi times this product. I needed everyone before I to turn it down. OK, so I'm going to do a similar switching of sums. I can rewrite this in this form. I sum over the j's. This is the gain I get if I hire someone that's j or better. And you can just phrase this as, I get this gain from j plus 1 to j if and only if it's not the case that everybody from 1 to j wasn't hired. OK. So far, I always like to say, like, equalities are easy, right? If everything's an equality, even if I'm going through the switching of sums fast, you can trust me. The equalities we can figure out. OK, so nothing's happened yet. Really, nothing's happened yet. OK, so this is the first step where something happens. I'm going to say that the expectation of products is less than or equal to the product of expectations, which allows me to write a greater than or equal to because there's a negative sign here. And also, this term is non-negative. That's why I needed this sorting. Okay, so why is this? There's a very simple intuition that comes up often in sequential randomized rounding is the notion of like negatively correlated. So here it's just saying, okay, you should think of this as a bad event. This is the bad event that I didn't get anybody j or better. So these are almost independent. If they were independent, the expectation of the product would be the product of the expectations. They're not quite independent because remember, there could be those two y's where I rounded one up or rounded one down. But that only makes this bad event less likely because what that was telling me, if I didn't make an offer to candidate, say, 2, that means I did make an offer to candidate 3. So this bad event is less likely to occur than in the independent world. So therefore, I can put a greater than or equal to there. And then once I get here, this step is again equality. I'm just replacing this expectation. And here I'm using the independence. OK, the final step is the final step is to use a very common inequality, which is just 1 minus x is greater than or equal to e to the negative x. Sorry, that was the second final step. The final step is now also a very common inequality that often arises, which is, so what are we trying to do, right? I'm trying to prove that this is at least some constant factor of this. So I just need to compare these terms to these terms. What is this? I'm basically comparing 1 minus e to the minus x to x. This is going to be decreasing in x. And but I know that this sum, which is the expected number of people I hire, is at most 1, because k is 1. That was an LP constraint. So this ratio is minimized when this term is 1. And so therefore, every single of these terms is at least 1 minus 1 over e, which is the value of this at x equals 1 of this. And I'm done. And note that I did also end up having to use every single LP constraint. That's another sign that you did it correctly. I had to use the T constraint to show that the algorithm is valid, and I had to use the K constraint to make this step of the proof. OK, cool. So hopefully that whets your appetite a bit. So very simple. I want to emphasize one thing, which is this rounding algorithm. It returns a non-adaptive algorithm. What does that mean? I fix the sequence of offers beforehand, and I'm never changing, right? This is actually not optimal if k is greater than 1. The main intuition is if I have, say, 2 positions, how early the first one gets filled dictates how aggressively I can go for long shots on the second position. So this is not optimal. So in general, I can think of a picture like this, where this was the rounding algorithm I gave, which gives you a non-adaptive algorithm. The best non-adaptive algorithm is going to be better than that, but it's still going to be worse than the best adaptive algorithm that adapts the order depending on how many positions are left relative to time. And then the LP is an upper bound on everything. OK, so now I'm going to make an admission, is that the rounding algorithm I showed you is actually kind of stupid. Why is that? Because in this earlier paper, they show how to compute the best non-adaptive algorithm using DP. You can actually do this efficiently. It's not particularly hard. So because the rounding algorithm is giving you a non-adaptive algorithm, and you can compute the best non-adaptive algorithm using DP, you should never actually execute the rounding algorithm in practice. But this analysis was actually a very simple way to compare what's called the adaptivity gap, which is the best non-adaptive algorithm to the best adaptive algorithm. If you directly try to compare these two, it's in general very difficult, and that's what the previous paper did. And then, so this argument improves upon the previous guarantees, because essentially we're saying, OK, the best non-adaptive algorithm has to be better than this dumb rounding non-adaptive algorithm. And the best adaptive algorithm is no better than the LP. And this dumb rounding algorithm was purely designed to get this guarantee against the LP. So in some sense, this was not an algorithmic construction. It was more a simple way to compare these algorithms by using the right sequence of relaxations. OK. One can also show that this is kind of the limits of this argument. If you want to try to get a better adaptivity gap, you can't use the LP, because the gap between the LP and the best adaptive algorithm is the same factor. OK, So that demonstrates, this randomized rounding technique, it's not necessarily algorithmic. It can be for conceptual results. I'll now show you also randomized rounding. Another powerful thing is it tends to unify a lot of different problems. So I'll now show you an extension of the previous problem that can be solved in the same way. So this is now the sequential interviewing problem, where instead of having already interviewed the candidates, they now have random values. So I'm highlighting in red what's different from before. Everything's the same. The only difference is the WIs are now random. I assume I know the distributions. They're independent. Now I sequentially interview candidates. When I interview them, I assume I discover their true weight. And then I have to decide whether to hire them. In this model, I assume they always accept. They always accept if I make them an offer. Once again, I'm trying to maximize the expected total value of hires. I can make the most T interviews. So there's two variants of this problem. You might have wondered this already. Do I have to make hiring decisions right away? So these are called different things in the literature. If I can wait until the end of my T interviews and hire the K highest realizations ex post, this is called the probe top K problem. If I have to immediately make a decision after each interview, this is called the free order profits problem, where usually then I don't even have this constraint of T interviews. Because the problem there is hard, is non-trivial, even if I don't have a limit to the number of interviews, because immediately after I draw one of these random variables, I have to decide whether to commit to taking it or not. OK, and there's further subvariants. You can also optimize over adaptive or non-adaptive algorithms. OK, so now I'm going to tackle this extension using relax and round. The relax step, I'm going to write a similar program, but now I need two variables. So yi is the probability of interviewing I, and xi is the probability of hiring I. And so I have the same constraints before, that in expectation, I interview at most T people, I hire at most K people. Xi has to be less than or equal to yi, because I'm assuming I can't hire someone without interviewing them. Now I got to explain the objective. So I'm once again going to make this claim. The relaxation is an upper bound on any algorithm, even the most powerful type, that can delay all hiring decisions until the end and be adaptive. OK, so I'm going to talk through the proof again. Essentially, it's the same proof as before. The main thing is I have to explain what this term in the objective is. So basically what this is saying is, suppose I interview someone with 60% probability, Andres. I interview you with 60% probability, and suppose the LP tells me I hire you with 30% probability. Right? So this means half the time I interview you, I'm hiring you. What this is saying is, OK, what's the best value I can get from you if I'm hiring you half the time I interview you? It's basically whatever your average value is on the top half of your realizations. So basically, if I'm only hiring Andres half the time I interview him, then the best I can collect is basically like the average value on the better half of himself. And that's what this is saying. What I actually collect might be worse, because he might take a value in the better half of himself, but then I go interview Yachi or Angela, and they take really high values, and I don't get them anyway. So this is a relaxation. The actual thing will be worse. But nonetheless, you can't do better than this value, which is xi times this expectation on any algorithm. OK, so that's the relaxation. The round step is now, once again, I still solve this problem. And essentially, I'm going to reduce this to the sequential offering problem in the following way. So I'm just going to let pi, right? So this is the thing that I don't have anymore. But whatever the solution to the LP is, I just define my pi to be xi over yi. And I force my algorithm so that when I interview someone, if they draw a value in their top pi quantile, I immediately hire them. And once I place this restriction on the algorithm, it essentially becomes like a sequential offering problem, because it's just, I'm going to make you an offer with probability yi, and I'm going to probe you with probability yi. And when I do, pi% of the time out of my control, and you're going to, I'm going to hire you, because I've committed to hiring you with probability pi when I interview you. And this constraint just becomes the same as before now. It's xi is equal to pi yi by definition. And finally, I just have to define wi to be the expected value of capital Wi over the top pith quantile. And so this is just the same problem as before. I'm just basically, it's as if when I interview someone, pi% of the time, they're going to use up a hiring slot, and conditional on them doing so, I collect little wi on average. And this is exactly this objective, which is the same as before. So I just run the sequential offering algorithm from before with these values, and the same result will hold. And essentially now, note that in this sequential interviewing problem, I gave myself a non-delaying, non-adaptive algorithm, right? I forced my algorithm to be non-delaying. It made decisions right away. And it was non-adaptive, because it's the same argument. I'm still sorting, and I'm not adapting to how many positions are left. And this shows that you can always get the same approximation ratio compared to the best delaying adaptive algorithm. So unlike before, this is not just an adaptivity gap result. This is also an algorithmic result, because these more complicated versions of the problem you can no longer solve in polynomial time using dynamic programming. You can't optimize over non-delaying, non-adaptive algorithms in general. OK, one final thing. I kind of slid this under the rug. It wasn't obvious that the, quote, the program wasn't actually an LP that you could solve. If distributions are discrete and finitely supported, you can reformulate it as an LP. You can also handle it if they're continuous using some minimax reformulation. But I did sort of hide one thing. It wasn't obvious that this was an LP, but hopefully you can trust me that it is, and you can solve it at least for discrete distributions. OK, so that's all I wanted to talk about for hiring. And so let me just give you a checkpoint of what we learned, right? So I tried to give you, this is not the most classical sequential randomized rounding problem, but I like it because it's a very simple one in my mind. The proof is quite short, at least for k equals 1. We got a flavor, and we also saw one aspect of sequential randomized rounding where we kind of gave a unified treatment of a lot of things. Offering was the same as interviewing. There was both this computational result and this adaptivity gap result, because the algorithm we derived was really dumb. It didn't delay, it didn't adapt, and the upper bound happened to work even if the algorithm could delay and could adapt. So now I'm going to study a slightly more complicated problem, stochastic knapsack, that expands on some of these concepts. OK, so stochastic knapsack is the following problem. I now have jobs instead of candidates. I'll change the wording. They have random values, but they also have random processing durations. These are drawn from known distributions. They're independent across jobs, and I'm going to assume the processing duration is an integer. I have one server and t time steps to process jobs. I'm assuming I can't cancel a job once I start. When I sequentially decide the next job to process, wi and di are realized. And my objective is to maximize the expected total weight of completed jobs. OK, so here, this problem was first studied in 2008 in a setting where wi and di are independent from each other. And there, this paper contains a lot of nice results based on an LP that didn't look too different from the LP I showed you for hiring. Essentially, it only constrained the jobs selected by the LP in terms of total processing duration. So in 2011, there was a nice paper that studied wi and di being potentially correlated. And a key discovery here was that once the wi and di can be correlated, you can't use the simple LP anymore. You need to write a tighter LP, a more complicated LP that, quote, schedules jobs. Essentially, the intuition is you could have jobs that only return a high value when the duration is also very long and you manage to complete it. In that case, there's only a purpose of starting that job if you have enough time left so that there's a chance that job takes its long processing time and takes its high value. So you can't use this small LP anymore. It'll have an exponential gap, actually. Unbounded gap. So you have to write an LP that schedules jobs. So I'm going to now show you an improved form of this LP. And so now my decision variables aren't just which jobs I'm going to process. It's when I'm going to start each job. So now it's YIT. This is the probability of starting job I at time t. So these constraints say I can start each job I at most 1 time t. All right, so I got to explain this constraint. Essentially, this constraint just says the expected number of jobs processing at each time t is at most 1. So this sums over jobs. It counts both the jobs that I'm supposed to start at time t and all the jobs that I started at times u before t that are still not finished processing at time t. All right, and what's the objective? The objective is, because there's no cancellation, once I start a job I at time t, the expected value I collect from it is just wi times the indicator that it finishes on time, the expectation of this. OK, so one can again talk through the same argument to show that the LP provides an upper bound, so I'm going to skip that. And so I'm going to now just try to compare to the LP optimal objective value. I take an optimal solution to the LP. OK, so my goal here will be a bit different now. I'm going to try to replicate the LP solution exactly. So the algorithm's goal will be to start every job I at every time t with probability exactly YIT over 2. And if I can successfully do this, then I can always earn at least half the value of the LP. Because the value of the LP is just what I would have collected if I start every job I at every time t with probability YIT. OK, so now I'm going to try to prove to you that this is possible. And once again, the argument will fit on one slide. So my goal is to start every job I at every time t with probability YIT over 2. And I'm going to prove it by induction. So at time 1, my LP constraints say that in expectation, I can try to start at most 1 job. So therefore, if I just half the time do nothing, half the time start a job according to this probability distribution, I'll successfully start every job I at time 1 with probability YI1. OK, good. So now I'm going to suppose I did this for all previous time steps, and now consider a time t. So this is my induction hypothesis. OK, so the argument is now consider any job I that I'm trying to start at time t. So I'm going to try to lower bound the probability that I can start I at time t. OK, so what can prevent me? What can block me from being able to start I at time t? Well, there's 2 bad events. The first is that the server is busy at time t. I'm currently processing another job that I started before time t, so I can't start I. The second bad event is I already started job I, and it already finished, so therefore I can't start it at time t. So I should emphasize, I can only start each job at most once, and that's, again, why this problem has an exponential state space, because I have to keep track of which subset of jobs I haven't started yet. OK, so here I'm just taking a union bound. I'm just doing 1 subtract the sum of probabilities of these 2 bad events. OK, so let's try to analyze them. And the way we analyze them is actually very simple. Basically, we use the independence of the processing durations. So I should say, here I'm allowing for dj to be correlated with wj. But the dw vector still has to be independent across different jobs. So therefore, I can just essentially replace this expectation of product with the product of expectations. And this is, once again, just equality. So I'm not going to explain it in too much detail. This is simple. And here I'm just applying the LP constraints. So another check when you're doing this is you have to be using all the LP constraints. If you're not, then something is wrong. Here so this is basically just the probability of me starting something before time t and having it still be running at time t. Basically, this is just 1 minus the sum of jobs that I'm supposed to start at time t. Because the LP had a constraint that the total jobs that are either processing or starting at time t is at most 1. And this is just saying the probability that I could start job I at any time sums to at most 1, so that's at most 1. So this is just 1/2 here. And then the last equality is just algebra. OK, so what have I done? I've shown that the chances that every job I can be started at this time t is at least this, assuming my induction hypothesis. So now I need to try to complete the induction. And the argument goes as follows. Basically, so this says that the minimum over I of this is at least this. So therefore, I can kind of divide through and argue that the sum of these terms is at most 1. And why is this important? Because, OK, I think the easiest way to finish the argument is at each time t, my algorithm, I'm going to blindly, without looking at the state of the system at all, I'm just going to draw a job j according to this simplex. And then I'm going to start that job if possible. And by definition, this will complete the induction, because the chances that I draw job j is equal to this. And then the chances that I can actually start job j, meaning it hasn't already been started and the system is currently idle, is exactly the term in the denominator. That cancels out, and I get yjt over 2. OK, so finished. And OK, so here I swept something else under the rug. So I want to now illustrate another subtlety. So this works, but the algorithm that I defined is actually, it's not clear how you can do this. Because the way I sampled these probabilities, I need to know the probability that every job j can be started at every time t. If I actually wanted to keep track of this, I need to keep track of my exponential state space of which jobs have yet to be started. So this is actually a challenge. Usually the easiest way to resolve it is to do history sampling, which is, you can't analytically track this exponential state space, but you can sample executions of the algorithm's own history, do Monte Carlo approximation, and you sometimes need to make an argument. In this case, you do that the error propagation isn't too bad. So essentially, if you sample enough times and the estimates are different by epsilon, then you only lose epsilon in the final approximation guarantee. OK, so that's another subtlety that does often come up. And I've swept it under the rug here, but I wanted to mention it. OK, so that's stochastic knapsack. Once again, I'll try to illustrate sort of, you could say, the abstractness and the generality of randomized rounding by arguing that you can actually generalize this argument to other settings. So actually, I assumed you can't cancel jobs. You can handle cancellation of jobs because you can extend these arguments to the Markovian bandits problem, which is I have a bunch of different Markov chains with rewards. They can even be Markov processes where different transitions take different periods of time. I have a budget of t pulls to switch between these different arms. And when I pull an arm, the Markov chain transitions, and I see the transition and then the reward. And so if I want a cancelable version of this job, I can still handle it. The Markov chain would just look like this, where if I run the job here and I go down this unfavorable path, I can choose to stop it. A circle means I can stop. But basically, you can handle these two different Markov chains, the one where you can't cancel and the one where you can cancel in a unified way. Coming back to the interview example, you can also build complicated examples where, maybe I interview someone. A third of the time, they're a superstar. A third of the time, they're OK. A third of the time, they're awful, and I never talk to them again. If they're a superstar, I can further probe them again, make them an offer. 0.1% of the time, they accept, but I get a really big reward. Otherwise, they reject. If they get to the OK state, then when I make them an offer, they only accept what's probability a half. They accept with a higher probability, but their reward's lower. And you can also use this to capture Bayesian bandits with discrete priors. But basically, this type of argument is very general. As long as you don't have a restless bandits instance where arms don't move if you don't touch it, and also as long as you have independence across arms, you can do this type of argument, sometimes with weakened guarantees. Okay, so that's all I wanted to say about the second section. So let me now just do another checkpoint. So what, in addition, did we learn? We saw an example of using a more complicated LP to prescribe the order. So both of these were examples where you could freely choose the order that you touch the element's I. In the first one, it sort of sufficed to just use a basic LP and sort by the weights. In the second one, it was important that we wrote an LP that could give you a guide on which jobs you needed to process first. We talked about the history sampling to determine your state distribution. So this came up. This was important. We saw unification again. And then finally, we saw this notion of exact, or what I call frugal replication of an LP solution. Right? So when I told you the YIT, the algorithm, its goal was to start every job I at every time t with probability exactly YIT over 2. And that's sort of what caused me to have to even do this state distribution. And we're now going to see this again in the online contention resolution scheme problem, this idea of exact frugal replication of the LP solution, where I want to follow some scaled version of the LP solutions, no more, no less. OK. So I'll first now try to illustrate this through an online fair allocation problem. Because as you can imagine, this type of frugalness where I'm trying to give everyone like the same probability of acceptance relative to some LP value, it can have a fairness notion. So I'll now illustrate an online fair allocation problem where I have this mobile food pantry. I start with 1 unit of food, and I'm driving around to cities. So let's say I drive to the first city. I see the demand is 0.7. I need to decide how much food I can allocate to that city. I don't want to give up all my food yet. So let's say I only allocate 0.5. Then I drive to the next city. This is a small town. The demand's 0.3. So maybe I just serve everybody. I have 0.2 remaining. I drive to the last city, and the demand's 1. This was the biggest city. And unfortunately, then I can only give them 0.2, which is a very low ratio for the last city. And then I finish my route at the end of the day. OK. So the initial supply is 1, infinitely divisible. I visit the cities in some order. I see the demands. And I have to immediately decide the allocation. The allocation can't exceed the demand, and of course also can't exceed the remaining supply. And I assume the distribution for each DI is known and independent. OK, my objective here, let's for illustration purposes assume I'm trying to be fair in the following sense. I'm trying to maximize the minimum over cities I of the average amount I give them divided by their average demand. OK, so that's the problem. I want to now illustrate some examples of this problem, which will then lead us into the online contention resolution abstraction. OK, so here I'm just going to assume I have 2 I's. Each of them is Bernoulli 1/2. So you should think of these more as agents instead of cities. Basically, I have 2 agents. Their demand is either 0 or 1, each equally likely. OK, so let me now illustrate this problem, what a naive algorithm would do, and I'll explain why it's not optimal. So if your algorithm is naive, at the start you have 1 unit of food. For the first agent, half the time their demand will be 1, so you're going to give it to them, and you'll have no food left. The expected allocation to the first agent is 1/2. But then, only half the time, the food remains for the second agent, and now you can only serve the second agent both if the first agent didn't want the food and the second agent wanted the food. So you actually only allocate them in expectation 1/4 of the food. And 1/4 of the time, you don't allocate the food to anyone. So this, in terms of fairness, is not good, because the minimum of these is basically not fair to the second agent. You're only allocating them 1/4 when their expected demand is 1/2. It is maximally efficient. You are, with probability 3/4, allocating all the food. But in terms of fairness, let me now show you the optimal algorithm for this problem. And essentially, it's to be fair to the second agent, you can't always give the first agent the food when they want it. What I'm going to do is I'm going to, even when d1 equals 1, I'm going to set a1 equals 1 only with probability 2/3. And then I can redraw this diagram. So the chances that I give the food to the first agent is then 2/3 times the chances they want it. 2/3 times 1/2, which is 1/3. So their expected allocation is 1/3. 2/3 of the time, I'll have the food left over. And then, since it's the second agent, it's the last one. I'll just allocate them the food with probability whenever they want it. And then I can see that the chances I allocate to the second agent is also 1/3. So this was kind of the probability that exactly balances the two agents. It's not hard to solve for. You lose a bit of efficiency, but at least in terms of this max-min fairness, you get 2/3. Both of these ratios are now 1/3 over 2/3. They're balanced. OK, so this now hopefully whets your appetite for this type of fairness problem. I'll now show you the general solution to this problem for Bernoulli's, which uses this idea of frugal replication, and it's actually very elegant. So let's assume all the demands are Bernoulli with xi. This is what the algorithm would do. It's essentially just calculating and calibrating these probabilities so that it's perfectly fair to everyone. So when visiting I, if the demand is 0, or if you've already given the food away, you have no decision. You can't do anything. So you only have a decision if both di equals 1 and the food still remains. I'm going to set ai to be 1 with probability this, where 1 over gamma equals this. OK, so you'll see why this was the right probability when in the proof things cancel. I should just note, it's important when you're doing this type of algorithm to check that you're not falsely trying to set a probability that's greater than 1. And that's kind of why 1 over gamma is set like this, so that the denominator will always be at least 1, because even when I is the last person, n, the denominator in that case will be exactly equal to 1. So essentially, this was the largest gamma that you can get a valid guarantee. And so the theorem is that this guarantees this fairness ratio of gamma, which equals this. And so unsurprisingly, the larger the total expected demand, the smaller the guarantee that I can give to everybody of the chances you get served conditional on you wanting the food. OK, so the proof will fit on the rest of this slide. It's, again, by induction. I'm just going to show you that this can be achieved. It's also not hard to see that it's best possible. So why is this a valid algorithm? So the probability that agent 1 gets allocated, in other words, the expectation of A1, is simply, I need 3 things to happen. I need the supply to still be there, I need their demand to be 1, and I need this additional factor to be 1. So this term is 1, this term is x1, and this term is gamma by construction, because this subtraction is 0. OK, so suppose I've successfully done this for all past agents. Now consider an agent I. So then the chances that the supply remains for I is simply 1 minus the sum over previous agents times gamma xj, because these are mutually exclusive events, and the chances that I allocated to each previous agent j by induction is exactly gamma xj. And then the second term is xi. The third term is exactly what makes this cancel and equal gamma xi. And that's it. That's the main idea. We're done. OK, so I wanted to whet your appetite with this food allocation problem. So now I'll formally describe what is an online contention resolution scheme. So it's basically a more general version of this food problem. And so in the online contention resolution scheme problem, I'm now going to call my agents elements I from some set n. I'm going to think about wanting food as being active. So every I is active independently with a known probability xi. Instead of thinking of me visiting the agents, I'm now going to think about the agents as arriving. That's the standard terminology in the literature. So elements arrive sequentially. When an element arrives, I see whether it's active, and then I have to immediately decide accept or reject if it's active. If it's inactive, I can't give it food. There's nothing to do. So there's going to be some general feasibility constraint that defines what are the subsets of agents that I can simultaneously accept. So this will in general be downward closed. This basically just defines, OK, I can't serve too many agents. This just tells me what is the subsets of agents that are feasible to serve. And in general in this problem, there's going to be some polytope relaxation of f. I'll give you examples momentarily. And I'll just say, without showing you the reductions, is that the reason why people care about this problem is you can reduce, say, the previous fairness maximization problem, even under other fairness objectives. You can show that the worst case essentially is Bernoulli demands, and it'll fall in this OCRS framework. And in a lot of max weight Bayesian selection problems, you can also reduce it to this problem. And so in this problem, because I'm comparing against some benchmark, I can make some assumptions on there can't be too many expected active elements that overwhelm me. Right? So in the previous food problem, I gave you an arbitrary demand, but then my guarantee got worse if the demand got too big. Here, because I'm comparing against some optimum, in this formulation of the problem, you usually assume that in expectation, you can actually accept everybody. So this is studied under different types of constraints. The simplest one is a k uniform matroid, which is just I can accept at most k people. So the feasible subsets is any subset of size at most k. In that case, the fractional constraint is the sum of the xi's is at most k. So here are some other studied ones. Knapsack, where each I has a fixed size di. You have a knapsack, you can accept a subset of elements if their total size is at most 1. And the fractional relaxation is just the expected size of active elements is at most 1. OK, so matching. This is one where the elements are edges in a graph. You can accept a matching, which means you can accept at most one edge incident to any vertex. So you can't accept a subset of edges if two of them collide on the same vertex. And then the polytope is just the expected number of active edges surrounding any vertex can be at most 1. And classically, these problems were studied for general matroids, where f can be any independent set in the matroid, and pf is the matroid polytope. I'm not going to formally define them here. OK, so these are some examples. So what is a contention resolution scheme? So generally, a gamma selectable OCRS is an algorithm that can accept every element I with probability at least gamma xi for any f in some class, where class is one of these, and any vector x that's feasible in the polytope. So you can think about x as being chosen by an adversary. If you can satisfy this for any x and any f in some class, then you call this a gamma selectable OCRS. In general, the OCRS, it'll also depend on the arrival order. So if you have to visit the cities in the same order every day, that's the hardest to maintain this type of fairness. If you can visit the cities in a random order, then it's easier. OK, so let me now just give you some history on this online contention resolution scheme problem. It was first introduced in 2011, actually not as an online problem, as an offline randomized rounding problem with an active constraint. So what that means is, traditionally in these polytopes, if you're allowed to just arbitrarily round elements up or down, a lot of them are actually integral. So like, for example, it's like celebrated results that the matroid polytope, you can actually take any fractional solution and write it as a convex combination of independent sets in the matroid. For matching, the fact is true for bipartite graphs. So this paper introduced the notion that for each element, you can't just freely round it up or down. Basically, you first see whether each element is active independently with probability xi. But you see all the elements. And then, seeing all the elements, you can choose, let's say, the independent set that is feasible. But you're still trying to satisfy this guarantee in expectation. So this was the first occurrence of a randomized rounding of this form. It was offline. it was motivated by submodular optimization, and it's related to this concept of correlation gap, which, as I said, is distinct from integrality gap. Because for a lot of these cases, the integrality gap is 0 or is 1 or whatever. There is no integrality gap, but you still have what's called a correlation gap in this offline rounding problem, because you have the constraints. So OK, so online contention resolution schemes were introduced in this paper, which is a form of sequential randomized rounding. I see the elements one at a time. I see whether each one's active, and I have to immediately decide whether it's active, whether to round it up or down. I'll just say this is a very active area of research. I'm going to quickly just flash some references here. In general, matroids are reasonably well understood. Matchings is very wide open, where very few tight guarantees are known. Knapsack, some guarantees are known, but for some arrival orders, but not others. What I'm going to spend the remaining time showing you is the form of the optimal algorithm for k-uniform matroids, because I think this illustrates sort of the final take-home point I want to give about sequential randomized rounding. OK, so I'm just going to now illustrate. It's the same food problem, but now I have 2 discrete units of food, and I have 3 agents. And I'm going to assume the first agent always wants food. x1 is 1. And the latter 2 agents each want food with probability 1/2. So note that this is feasible, because the expected number of people who want food is at most 2. OK, so in expectation, I can serve food to everyone. But what is the best actual guarantee? So I'm going to now describe what the algorithm looks like. And this conveys a lot of intuition on designing OCRS. So the optimal algorithm, I'll tell you now that the guarantee is 3/4. You'll see at the end of the proof how to come up with this constant 3/4. For this instance, the optimal gamma I claim is 3/4. And once I tell you this, the design of the algorithm is actually quite easy in the first step, right? I've told you you need to give everyone food with probability 3/4 when they want it. So that means, so the first agent always wants food. That means I got to give food to them 3/4 of the time. There's no point to do better than 3/4, because I already sort of told you you're just aiming for 3/4, right? So you save both units of food with probability 1/4, but you flip a coin 3/4 of the time you serve the first agent. OK, so the second agent, this is where the subtle part comes. You now have a decision, because I have to decide, I need to serve them 3/4 of the time when they want food. But I can choose between serving them when I have both units of food remaining and only serving them when I have 1 unit of food remaining. And what I'm going to do, hopefully this is intuitive, I'm going to serve them when both units of food are remaining. I'm going to prioritize that. So what does that mean? When both units of food are remaining, I'm going to always accept them when they're active, which means 1/2 of the time when they're active, I'm going to serve them. 1/2 of the time I can't. But then when I come back to the sample path down here, I don't need to always accept them anymore when they're active, because I've already served them with some probability up here. And you can actually compute that when they're active, the second element, and I have 1 unit of food remaining, I only need to serve them with probability 2/3. So then the probability I accept them on this sample path will be 2/3 times x2. And then I can calculate that the total probability I accepted to is 1/4 x2 plus 3/4 times 2/3 times x2, which gives me exactly 3/4. So the 2/3 is just calibrated to make this work. And then now you can see why 3/4 was the best possible guarantee, because then the chances that I have food remaining to serve the third candidate is going to be the sum of these 3 sample paths, 1/4 times 1/2, 1/4 times 1/2, and 3/4 times 2/3. This is exactly 3/4, which means, for the last candidate, I don't have to hold back. So I serve them whenever they want the food, and I can serve them with probability exactly 3/4 times x3. OK, but how do we know this was optimal? So now I'll just describe the final slide. The way that you show this is optimal is you can actually formulate the optimal guarantee derivation for a fixed instance of this k-unit matroid OCRS problem using an LP. The LP essentially looks something like this. It's quite simple. Basically, you just have BLI. This is the probability that you have L units of food remaining when agent I arrives. Okay, so this works for a general k and a general number of agents. And the logic for these variables is just it updates the state variables following the transitions of whether you accepted someone. And then alpha Li is going to be the probability that you try to accept I when you have L units remaining. And you should think about this as an unconditional probability, so that the total probability I try to accept I is going to be equal to gamma, so therefore the probability that I actually accept I is going to be gamma xi, because I only accept them when they actually are active. So you can only set alpha Li to be non-zero if L is at least 1. Okay. So essentially, you can prove using LP duality and complementary slackness that an optimal algorithm satisfies a form like this. What does this say? This is essentially the intuitive rule, sometimes called a Lie's rule, dating back to that original work, saying you should always accept an agent. You should first try to accept them on sample paths where you have more units remaining instead of fewer units remaining. So this is just a formal way to prove this. And this is just saying when you're trying to satisfy this constraint to serve agent I with the right probability, you should always start with the k units remaining, and then k minus 1 units remaining, k minus 2 units remaining, et cetera. So you can prove this using this LP, and then this paper shows that once you know that the optimal algorithm satisfies this form, you can characterize the worst case instance and characterize the tight guarantee for a k uniform OCRS. And it says the worst case instance is essentially Poisson, which is often the worst case when you have a bunch of small probabilities, but in expectation, the total number of active elements is k. Okay, so I wanted to illustrate this because I wanted to sort of now end with what I call sometimes the fundamental theorem of sequential randomized rounding, except it's not really a theorem. It's more of an intricacy. Okay, I'll jump down. Okay, I'll jump down to describe this. Okay, so at first glance, this seems like a weird algorithm, right? Because basically, I mean, I've shown you several of these algorithms where your algorithm needs to track the probabilities of all the parallel states you could be in at any given time, right? So at any given time, you have some number of units L remaining. But when you're deriving these algorithms, you care about this probability distribution beta Li that tells you the probability of having L units remaining when you approach agent I. And importantly, the action that you take in one of these states, which is given by alpha Li, depends on the hypothetical actions that you would have taken in other states that you could be in at that same time. So, if you come from like a dynamic programming background, this is like very weird, right? Because you should only care about the state and how to maximize the expected value to go from that state going forward. You don't really care about how you got to that state or like what's the probability of being in that state by definition of state. But here, because we're either trying to prove some kind of approximation guarantee in expectation or provide a fairness guarantee in expectation, we do by definition care about the probability that I'm in my current state, and I need to make decisions for all the possible parallel states I could be in at a given time, sort of in conjunction. And that's what I call the fundamental intricacy of sequential randomized rounding. Okay. So let me now wrap up. And so, okay, so hopefully these are the learnings that I hope you'll take away. So just to reiterate, I think this most non-intuitive thing, if you're not used to sequential randomized rounding, is this notion of state tracking. It's like looking back on your past decisions. You need to care about what's the probability I'm going to be in this state. And ending on a more philosophical note, I used to actually be a poker player, and I often like to do this in real life as well. It's kind of like you can look back on all your previous decisions and ask yourself, what's the probability that I'm where I am right now? And obviously, it's hard to like quantify in real life, but I guess personally, I do believe life has a lot of chance. And I often tell my students, like, you can't control how many papers are accepted, but you can control how hard you work and how many expected papers are accepted, right? So you shouldn't just look at how many papers you have accepted. You should look at the distribution of papers that you have accepted, like the expected number of papers, to like decide, evaluate whether you're being productive. So, okay, so I'm not saying you have to do this in life, but at least for this type of algorithms, this is very important if you're trying to prove these fairness or expectation guarantees in expectation. And to do state tracking, you might have to do history sampling. And unfortunately, you can't do that in real life. I can't resample my history and make the same decisions I did. OK, second takeaway point, I guess also with some analogy to real life, is you let the relaxation guide you in this summary of learnings, right? So you write the relaxation. The variables in the LP have some meaning, and you use those to guide your decision. In some problems, you want to try to exactly replicate them, like in the stochastic knapsack or the OCRS problem. In the first hiring problem, you didn't have to exactly replicate them. And finally, this is almost an oxymoron in real life, tighter relaxation. I don't think that's a good way to relax, but it's a good thing often. For stochastic knapsack, we needed this tighter relaxation. You can't relax too much. You need the variables that are time indexed that tell you when to do what. OK, and finally, I talked about this unification nature of sequential randomized rounding. And often, a lot of problems all look the same under the abstraction of sequential randomized rounding. For example, aside from the hiring and interviewing versus offering unification, if you're familiar with online resource allocation problems, all these decisions, like whether you're making accept-reject decisions or pricing decisions or assortment decisions, they all end up looking the same if you do this type of analysis. So you can do one proof that gives you the same guarantee for everything. I've been saying this as kind of like a good thing for the technique, but I should also admit, this isn't always a good thing, right? This shows, like, you could say in some sense, a weakness of the analysis, that all of these problems are the same in terms of worst case approximation ratio using sequential randomized rounding. But for practical instances, you might want an algorithm that's specialized to pricing instead of assortment. And so it's a good thing and a bad thing. But generally, under this abstract nature, a lot of different decisions all look the same. OK, this tutorial was largely theoretical. Let me just quickly describe some applications of randomized rounding in practice. First, in e-commerce fulfillment, this has been shown to be used. Some, but not all, randomized rounding algorithms are very fast and parallelizable. That's one benefit. And that's one general benefit of randomized algorithms. And also the fact that these algorithms are simple usually mean they're more robust to things like distribution misspecification. Second, even though we're optimizing for worst case guarantees, there is some research that shows, even in terms of average case performance, these randomized rounding algorithms can perform very well. Again, in some but not all settings. I don't want to say this is the only way to design online algorithms. Definitely there's other settings where other works show that different, like say, primal dual ways of designing online algorithms can outperform randomized rounding. So, but I'm saying it's inconclusive, but there are settings where, even in terms of average case, you want to do sequential randomized rounding in online matching. And finally, coming back to fairness, for probabilistic fairness, there has been usage of offline randomized rounding in this Nature paper from 2021. And I think it would also be very interesting future work to consider online randomized rounding settings when you have to select citizens' assemblies in an online fashion. OK, so not everything I presented was my own results, but the things that were my own results are joint works with my fantastic collaborators. And I should finally say, my postdoc, Callum, is on the job market this year. And he's going to actually, in 30 minutes, if you want more advanced sequential randomized rounding, he's going to talk about OCRS for the matching polytope, which is probably the hardest version of OCRS, today at 4 p.m. in 337, Summit 337. And he's also on the job market this year, so please do check him out. So thanks again. It's been a real honor to be able to give this tutorial on sequential randomized rounding.